Okay, let me get going here. So let me talk first of all about the bonus. I felt like, sometimes I finish out a lecture and I leave and I feel fine. I don't think about it again. And other times I'll have a lecture and it just doesn't sit right. In our last class, it just didn't sit right. I don't think I could have gone to bed that night without resolving that issue. So I posted the solution to the bonus problem on YouTube on Tuesday. The whole problem worked out. So if you went and looked at the videos that I put up on Tuesday, the answer to this problem was there. So anyway, it was there. Whoever found it, found it. But I really wanted to make sure that you understood that problem, I think if you look through the answer, you'll see why I didn't do it in class. It's a lot of work. Now, it's not that, this is a bonus problem, like this is too difficult. It's just too time consuming. And so what we're going to see a lot of even today is that a lot of times what we're going to try and do is just get an integral to a place where we know how to handle it from there. And then just kind of wave our hands at it and say, yeah, we could do that now. Okay? Am I making sense? Like the way I look at it, if you did your homework for 6.2, right? If you did that, then if we can get an integral to integral cosine squared theta d theta, we'd be done, right? If we could. So we're going to kind of keep building on things. Now, some problems today I will take all the way. Others I'll just wave my hands out and I'll just, understand, wave hand, just say, okay, do that later. Yeah, so that's it on the bonus. Let's talk about this. I'll post all this so you don't have to write this all down, but I told you in the margin of the book, they summarize like how to attack these integrals. I put it down here on paper. If you have sine to the m or cosine to the m or a combination of sine and cosines, what do you try? So here are the hints. This is just right out of the book, okay? And then here's how you deal with the secant and tangents when they're together and what substitutions you make. The green over there in the side is telling you what substitution you'd make. All right. Now, I was very tempted today to come around and do a homework check and give you a quiz grade. So how about, because I would like to offer people, that's a free 100 if you did your homework, right, on a quiz. So let's just take a real quick vote. How many of you would like me to come around and give you 100 based on your homework? That's it's about, okay, well, I'll consider it. I'm not sure yet. I hope the lesson's been learned. I hate saying the same thing. I feel like a scratch record, but it's your grade. So got to do your homework. All right. So those are the methods. Now today, what we're going to do is a completely different method. Well, not a completely different. It's kind of a new technique. It's still in the same section of the book. But the reason it's in the same section is because a lot of times when we do this new technique, the new problem turns into like a cosine squared theta or something like that. So they put it in the same section. This technique is called Trig Substitution. This is what I ended the last class with. And really the question is, when do you use this technique? And what we'll be looking for is integrals that have square root of a constant squared minus our variable squared, square root of a constant squared plus our variable squared, square root of our variable squared minus a constant squared. Anytime you look at an integral and you see something like that in the integral, this technique is light bulb should go off and go, trig substitution might help me here, all right? These square roots do not have to appear by themselves. They can just be part of the integral. It can be in the numerator or denominator. Just anywhere in an integral you see something like that, trig substitution should come out of your, somewhere in there. Also, and the book doesn't talk too much about this, if you see any of those forms without the square roots, trig substitution may help also. All right? So we're looking for number plus our variable squared, number minus our variable squared, or variable squared minus a number. Okay? Now the question now becomes, what do we do, right? What is trig substitution? So my next page, again, you'll be able to print all this out later. These are the substitutions. The first one, if you see an integral with a squared minus x squared, that means you have a number minus your variable squared, somewhere in the integral. You can always replace x, the x you see there, make a substitution, x is a sine theta. And let's try and make sense as to why that's going to work. So if x is a sine theta, a is a constant, right? What's the derivative of a sine theta? A cosine theta d theta, right? Now I take the x and I square it. So I square the a and the sine, right? So that's just algebra. What happens if I take a squared and subtract that x squared? So what I'm trying to do is get it to look like what's up there in the green. A squared, take away the x squared. That's a squared. Take away this. Do y'all see it? Now, what's the square root of that? Well, it's the square root of that. And now from here, what did I do to get to that next line? Yeah, from here to here, I factored in a squared out of both terms. And then I took the square root of a squared, which is a on the outside. And what's still left in there is the 1 minus sine squared theta. But 1 minus sine squared theta is cosine squared theta. And the square root of cosine squared would just be cosine. So the stuff in yellow is what you should pay attention to. If you have that green thing, x will be a sine theta, dx will be a cosine theta d theta, and the square root of that junk that you had to start the problem with, way up there, the green stuff, will turn into a cosine theta. You don't have to go through all this work on every problem, as long as you remember these three things. Okay? That's what you do if you see square root of a squared minus your variable. What if you see square root of a squared plus your variable squared? You don't do a sine theta. This time you do a tangent theta. And you can go through the same construction. The derivative is here, square it here, add the a squared, take the square root. It's the exact same thing that we did before. Work that out, you get a secant theta. And then the last one would be if you have your variable squared minus your number. And this one, you let x be a secant theta. There's your derivative. I didn't even show all the work. And then here's what that root would turn into, a tangent theta. Okay? Yes? It's not on your formula sheet, right? So let's say for now you need to think that you're going to need to know it. Yep. In the past, I have let people just write this down on tests. But I'm actually considering like one formula, like one, you make your own sheet for this next test. Like no worked out problems, but just whatever reference material you think you need. And that, yes. Yeah. Because, you know, we are kind of getting to the point where you have to be realistic. Like in the real world, you face a problem, it's not like you have to sit in a room and you can't do anything, right? Like you can't look anywhere, right? I mean, you have to be resourceful. So I want you to learn a little bit about how to create something that you can work off of, right? Your own stuff. So yeah, I mean, just but try your best to try and get these things hardwired. All right, any questions on how the construction of these or anything? You ready to see how they work? Yeah. You'll see. Yeah, we're going to have a real clever way of dealing with it when there's no square root. Yeah. One question that might pop up is like, which one is this? Which form is this? What would my substitution be on that one? The first one, right? Because I have my constant minus my variable. So what would A be in that problem? 2. Y'all okay with that? Yes? Okay, yes? No. That was going to be my next question. What's this then? A is root 3. It's the square root of 3. Because a squared has to be, see, this is a squared, right? That means a is root 3. So you look at it this way. If you have a number plus your variable squared or a number minus your variable squared, whatever that number is, the square root of it is a. So if it's 4, then obviously it'll become 2. But if it's 3, it's root 3 because it's not a perfect square. Is that okay? Any other questions on that? Yes?
What if this variable plus
Well, we would use the second one here, right there, because that's the same, because addition doesn't matter. And that's why I was kind of I was trying to lead to this. What's the difference between, I mean, are these two things the same here? No, they require different substitution, don't they? So some people say, well, why don't I just take this and factor a negative out? And if I factor a negative, it becomes the 4 minus x squared, right? I kind of switched the order, but do y'all see what I did there? That's fine algebraically to do that, but here's the problem. That negative is really like a negative 1, right? How can you get a negative 1 out of a root? You need imaginary numbers. And, uh-oh, my book. Oh, no. I left it in my other classroom. I was just going to make a visual illustration. This entire book does not involve imaginary numbers. This is all, if you read it, well, it doesn't say it here, but this is calculus of a single real variable, meaning that everything we do here, our variables are real numbers. So we can't deal with this. Now, there is calculus with imaginary numbers. That's called complex variables. There's complex analysis. That's a whole different ballgame. Okay? All right. I think we're ready to get on here. I can't believe I forgot my calculus book. All right, I think what I'll do is I will start with one of our favorite formulas. There it is. How about we address this? We've seen this for a long time, and we know how to deal with it. But now it's time to figure out where it came from. Right? Everyone should look at that and automatically be saying arctan, right, is the antiderivative. And on a test, you could say arctan. This is just demonstrating how this trig substitution works and how the formulas for these were obtained. All right? So what I notice right now is I can't do a basic substitution. I can't do anything just real simple, okay? It's, right, if I didn't have that formula, I would be trying other things, right? So you need to see that square root in there of a squared plus x squared. So I'm going to make it happen. And Jacob, this is what you were talking about here. What happens if there's not a square root? Well, if there's not a square root, you make a square root. You see? Now I have something that looks like square root of a squared plus x squared, don't I? Where a here for us is what? 1. And what is the substitution that we make when we have a squared plus x? It's the second one, right? I don't need to flip back. Everyone's okay with this? So now I'm going to come here. This is my integral I'm working with here. Here's my substitution. I'm going to replace x with a, which is fortunately 1 for us, but I'll put it a tangent theta. Yes? What's dx? Secant squared theta d theta. You can do that without needing anything to reference, right? You just take the derivative. The rest of it, though, you might need to reference the sheet. Now, you're asking, can we have these written down? I personally don't have them memorized. I'm not big on memorization. So what I do is, when I do these problems, I just construct it real quick. I just write down, okay, what's x squared? That's just tangent squared theta. Okay, what do I have underneath my root? I have 1 plus this, right? Now I take the square root on both sides. But what is 1 plus tangent squared theta? Secant squared theta. So this is the same as square root of secant squared theta, which is secant theta. So I would not need all that work, okay? You could just write down, this is what I would want to see. This, and that equals this. That's what I would expect to see on the test. All right, time to go do this now. I'm ready to rewrite my integral. Here it comes. Integral 1 over, now what is the square root of 1 plus x squared? Secant theta, but what am I going to do with that? Squared. I'll put the squared on the outside. But what's dx? Secant squared theta d theta, right? What? Secant squared thetas are going to cancel, right? Any questions on it, though? We're good? So this becomes integral 1 d theta. Is that it? Right? Secant squared of secant squared is 1. Or just d theta if you want. What's the antiderivative of 1 with respect to theta? Just theta. Plus a constant? We're not done. Because now what I need to know is what's theta. So now what I'll do is I'll go back to where I made my substitution. And here's where I made my substitution right here, right? I said x was tangent theta. So I'm going to write that down over here. But x equals tangent theta. So how can you take that equation and solve it for theta? How? Take arctan on both sides. So arctan of x equals the arctan of tan is just theta, right? So your answer is, if your answer is theta, and we just said theta is arctan, then the answer is arctan. And we're done. Kind of cool, huh? So this is tangent inverse x plus c. So I just proved the formula. What is this? All right. And we move on. New one. Just so you know, what I'm trying to do is this. Last spring, I had a calculus class, and I did problems in that class, right? I'm trying to not do those problems again. And I'm trying to, so that basically if I keep teaching Cal 2, eventually I'll have every problem in the book done, because I'm doing different ones on video, So the ones I'm picking are ones that are not on the other video. So just know that there are more problems straight out of the book that have been done on my other videos, if you want to go look at those. And then always the even solutions I've put out there. All right, I'm doing, I think it's number 42. Yeah, 42. So it's integral, this is a definite integral, 0 to 1, x cubed square root 1 minus x squared dx. Now, if I were doing this problem initially, what I would first start looking at substitution. Like, is there a substitution I could make? You know, if I let 1 minus x squared be u, what's the derivative of that? Negative 2x, and you have it negative 2x there. Hey, wasn't this on the exam? Was this the last problem on the exam? I'm thinking here that this looks so familiar. Where's your exam? There it is. It wasn't? The last problem? Oh, it was sine. That's right. It was x cubed sine x squared. Okay. My apologies. It looked too familiar. But I could maybe attack it the same way that one on the exam was. Where I peel off an x on the front, x squared. You know what I'm saying? Square root 1 minus x squared. I could maybe mess with it that way. But I'm not going to, because I want to try this trig sub. So do you have one of the trig sub forms here? Yes, you've got the, what, a squared minus x squared? And again, luckily for us, a is what? 1. It's not always going to be 1 today, all right? And so whenever that's the case, what's my trig substitution going to be? X is, if it's a squared minus x squared, what is it? A sine theta. And a is 1, right? So sine theta. That part of it you have to know. It's one of 3 substitutions. It's either a tangent theta, a secant theta, or a sine theta. Those are the only 3 trig subs. Hey, sine subtraction? Sine subtraction? Maybe you could remember it that way. I don't know. You figure out your own way of remembering it. But then what if you have it the other way around, right? It's x squared minus a squared. That's subtractions. Whatever. You resolve that yourself. Dx is what here? Cosine theta, d theta. And then I'm going to skip all the steps and just go right to this. That should be what? Just cosine theta? You might be asking yourself how I did that. So I'm just going to remind you this one last time, that what I'm doing here, I'm going back to this. I'm using that first substitution, which says that if I let it be a sine theta, that square root at the end is going to be a cosine theta. It's cut off on the screen here, but a cosine theta. Yes? Where? Right here? I just squared this, yes. Because what I'm trying to do is figure out what this green part turns out to be. So it has an x squared in it, right? So I square the x to get x squared. And then I write a minus it and then work through all that. And I'm not sure I understand your question. I can show it. All right, so I'm taking this, I'm squaring it. And then I have 1 minus it underneath that square root. And then I have the square root of that. But 1 minus sine squared theta is cosine squared theta by the Pythagorean identity. Right? That's the Pythagorean identity? Cosine theta. I failed to mention that maybe. Sometimes the things I forget, some things are more obvious to me than they would be to you. That happens a lot, doesn't it? All right. All right, so let's rewrite everything. Oh, wait, no, I'm not ready to rewrite things yet. Let's keep in mind, I'm going to make an indefinite integral. Right now it's definite, right? But I'm just going to find the antiderivative first. Then I'll plug everything in later. Let me do some switching around here. I have integral x cubed. What's x cubed? We have x, right? X is sine theta. Cube both sides. So x cubed is sine cubed theta. Y'all follow that? Times, what's the square root of all that junk? Cosine theta. Times, what's dx? And don't forget the dx, all right? Cosine theta d theta, which turns into integral sine cubed theta cosine squared theta d theta. Okay, let me match things up here. Your dx right here, right, is this, because that's this right there. And then the root is this, which is this, which is that. And then the x cubed is this. Fun with colors here. See it all? Now, sine cubed theta times cosine squared theta is homework material from last time. The way you would get that is to peel one sign off. Okay, I'll set it up, but I'm not going to work through it. I would peel one sign off, which would leave me with the sine squared theta, cosine squared theta. Here's the sign that I peeled off. Then I would switch my sine squared theta to a what? 1 minus cosine squared theta. And then I'd have cosine squared theta, sine theta d theta. And then I would distribute the cosine squared theta through the parentheses. Yes? Then you'd have a bunch of signs, but then they would all be to like different powers, and what you would not have is something in its derivative. So you wouldn't have anything to make a substitution with. See, what we're going to do here is we have this sine theta d theta. The reason we peeled that sign off is because that's the derivative of cosine. Well, off by a sign, but so everything else is going to be in terms of cosine, and I'll be able to make a substitution u as cosine. So I will say dot 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 because this is definitely homework from last time. Okay? Now, you probably want to know what would happen, huh? We have to plug numbers in. Oh man, I may not have a choice. Okay, this is going to turn into, let's see, cosine. So 1/3 cosine cubed theta, but it'll be negative, and then plus 1/5 cosine to the 5th theta. But my substitution was u as cosine, so the derivative is negative sine. So that I've compensated for the negative already. That's just the antiderivative. I'm not showing the work. That's just the antiderivative. We can check it. You could check it yourself. Okay. And then plus your c. But now I'm going to go back to the definite integral. Okay? So this is that's my general antiderivative. And now going back to the integral, the original problem, x cubed square root of 1 minus x squared dx from 0 to 1. Right now, look what I have. What's wrong with my expression for my antiderivative right now? It has thetas in it, right? It has thetas. And my original problem has x's. Well, you have to figure out what's cosine theta. What is cosine theta? Where do you go to find that information? You go up to your substitution. Let me go to my substitution. What was x? Okay. From that information, x is sine theta. I'm going to construct what we call a reference triangle. We talked very briefly last time about this, but we did do it. Put your angle in here, theta. Sine is which side over which side? Opposite over hypotenuse? So x and 1. So what I've done is I've drawn a triangle. That triangle says, if I look at that triangle and ask you what's sine of theta, you'd say x, wouldn't you? So I reverse engineered the triangle from the equation x is sine theta. Yeah? Now I want to know what cosine theta is, right? Cosine theta is the adjacent side over the hypotenuse. But what's the adjacent side? 1 minus x squared. Now, did anyone notice I could have gotten that from this line right here? Yes? You see it right there? What cosine theta is? But the reason I'm showing the triangle is because you won't always have what you're looking for up there. It won't always be there. So you need to get used to working with a triangle and generating the other sides. You'll always have two of the sides. You'll have to get the third one. So you might need to, put a question mark. If you don't know how I got that blue, then we can talk. All right, I'm out of room, but I'm going to go ahead and, what I'm going to do is I'm going to take that square root of 1 minus x squared right there. I'm going to replace both my cosines with it. Okay? Here we go, next page. So I have negative 1/3. It was the square root of 1 minus x squared, but to the third. Was it We'll take a vote. Was it positive or negative? Negative, okay. All right. So that's the cosine theta right there, but then being cubed and then the cosine theta to the fifth. Now I'm ready for my definite integral. Here it comes. Integral from 0 to 1 of x cubed square root 1 minus x squared dx is equal to this nasty thing evaluated at 1 and 0. Does anyone have a question on where any of this is coming from? Or where I got any of that junk there? Yes? Off that triangle? How I got it? Talk to me after class. No, it's all right. Just a squared plus b squared equals c squared. Solve for a. The hypotenuse, 1. Yeah, we'll talk. Okay, plug 1 in first. What do you get when you plug in 1? 0, that's good, right? It kills off everything. So plug in 1, you get 0, yay. Minus, okay, now plug in 0. Well, when you plug 0 in, that goes away and that goes away, and you just have 1s under the roots. Square root of 1 is 1. 1 to the third power is 1. 1 to the fifth power is 1. So those are just 1s, aren't they? So negative 1/3 plus a fifth. But that's being subtracted, isn't it? So this is really 1/3 minus a fifth, which is 2/15. What did I what? Right here, this. Because that triangle, if I asked you what's cosine of that angle, look at that triangle there. What's cosine? It's the adjacent side over the hypotenuse. The adjacent over 1 is just the adjacent. So cosine of theta is square root of 1 minus x squared. So that cosine theta gets replaced with square root of 1 minus x squared. Had that been, let's just say that had been tangent theta. Let's just say tangent theta cubed. It would be, you'd be replacing tangent theta with x over the square root of 1 minus x squared.
So that's not the cosine was the argument was theta.
We're replacing this. The whole thing, the whole trig function. All right. 2/15. Positive 2/15. All right, let's do another one. Integral dx over x squared square root x squared minus 16. So you might be, fumbling through some of your formulas, looking for something on this, or, we have some formulas that involve square roots, don't we? In fact, we do have one that deals with, if you look in the back, I believe we have a formula for this, don't we? Where you have 1 over just the square root of u squared minus a squared. You should have a formula for that. What is it? Is that a squared minus u squared or u squared minus a squared? Other way around. That's all right. Uh-huh. Do you see it? It has a u in front. See, we don't have a u in front. What I'm getting at, though, is in the book, those reference sheets, there are some formulas. And if you've got that form, do it. Do the formula. But if it's not, like this one is not, then you have to do something else. Okay. I think this looks like one of our forms, doesn't it? This? It's a plus in there? And it has an x squared out front? Yeah, see? Almost. Can't do it. Yep, can't do it. Well, then if you did a plus, you would have to factor a negative out, which would make your x squared negative. And then you can't get the negative out of the root because it's I. Okay, so this is the same as minus 16 is 4 squared, right? So we have that form, right? X squared minus a squared. So what will we what's a? Sorry, I should have said a is 4, right? So what is our substitution going to be when we have x squared minus a squared? Can y'all just nudge him or something? Just shake him. Hey. I slept 2 hours last night. I know I'm talking, so it's easier for me. You're out? Well, you can sleep on a bench outside. That's fine with me. Don't sleep in here. Okay? All right, so what is it? A what? Secant theta. Next one. What do you do after this? Dx. What's the derivative of that? Secant theta, tangent theta, right? D theta. Then skip all that other stuff. square root of x squared minus 16 turns out to be what? 4 tangent theta.
I didn't work it out. I just
Yeah, that's fine. You can do it right here. Look at what's x squared, everyone? 16 secant squared? If that's a 16 secant squared theta minus 16, you can pull a 16 out. Square root of 16 is 4. Underneath here still is a secant squared theta minus 1. What is secant squared theta minus 1? Pythagorean identity. It's tangent squared theta. Square root of tangent squared theta is tangent theta. Or just work it out. Yeah. Which I'm only doing this because I'm trying to skip the steps so you can do that however you're comfortable. But I'm not going to show it anymore. So that's what we get. Now let's go back and try and reconstruct the integral. My dx I've got here, right? My square root of x squared minus 16, I've got that here. But I still need the x squared, don't I? So just square x, right? Square x here. X squared is 16 secant squared theta. So let's rewrite this integral. Dx 4 secant theta tangent theta d theta. I'm going to tack the d theta on the end. Over x squared, which is 16 secant squared theta. And then the square root is times 4 tangent theta. Does everyone see where all of that comes from? We good? Yeah? Start canceling some stuff here. Let's see. I'm going to cancel the 4s here. I can cancel the tangents. And 1 secant on the bottom. I mean, sorry, 1 secant on the top cancels with one of those secants on the bottom, right? So the only thing I'm left with is a 1 on top, right? And then on the bottom, a 16 secant theta. So I have 1/16. I'm going to pull the 16 out. 1 over secant theta d theta. Do we have a formula for 1 over secant theta? Yeah, secant 1 over secant's cosine. So flip it. And this isn't even, I mean, this doesn't even require anything from this section. It's antiderivative cosine sine. So this becomes 1/16 sine theta plus a constant. Yeah, now we need to get everything back in terms of the variable, which was x. So we go back up to our information. See, our information tells us the connection. That first substitution we do will always be the connection between theta and x. That will always be what you use to create your triangle. Always. So here I come with my triangle. First thing, I'll write down what I have. Now, before I can draw my triangle, I need my secant theta by itself. So I'm going to divide by 4, which is perfect because that creates a fraction. And when I draw my triangle right now, and here's theta, Secant is the reciprocal of cosine, right? Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent, right? So what's the hypotenuse of this triangle? X. What's the adjacent side? 4. And then using the Pythagorean, a squared plus b squared is c squared, I'll solve that other side. Now I'll do it on this one because there's probably more than one person here that doesn't know how to get that side. So I'm going to call that other side here b, just for the hell of it. Could have called it a, could have called it b, could have called it c. Probably shouldn't call it x though, right? Pythagorean says what? 4 squared plus b squared equals c squared, which would, so a squared plus b squared equals c squared. I want to know what b is, so subtract the 4 squared, so subtract 16, right? And then take the square root on both sides. So b is the square root of x squared minus 16. That help? Okay. You do enough of these problems and you'll be able to do that without having to work it out. It's always the same, it always has the same format to it. Yes.
Like the other problem, the triangle, it's the same value as the denominator.
When I do the triangle,
That side,
mm-hmm. Mm-hmm. It is. It is. Yes, I think that's what you're saying. It's always that thing you started with? Mm-hmm. Well, I should say it this way. In every problem I've ever done, it is. I've never proven it generally, but it should be. But I don't want you to ever avoid the reference triangle. Okay, as long as you're comfortable drawing a reference triangle, that's a critical skill. It's necessary, and it brings things back from pre-cal. It's a good thing. We're not done. Hold on. So what is sine of theta then? Opposite over hypotenuse, right? Sine of this angle is opposite over hypotenuse. So I'm going to replace this. I'm coming back to this answer right here. I'll see the 1/16 sine theta. It's going to become down here 1/16, but sine is the square root x squared minus 16 over x plus c. Yes, we're done.
can I say, when I do the first substitution,
Mm-hmm.
I can get the triangle as well.
Oh, at the very beginning, you could have the reference triangle. Oh, right off the start. Uh-huh. The thing is, you don't know if you're going to need it later. You might not. Like in this problem, our answer was sine theta, right? We need it. Had it been tangent theta, we would have already known what tangent theta is. Or something, without a triangle. Yes? Where? Up here? This x equals 4 secant has to be secant. Because the form we have over there on the top right, we have our variable squared minus our number. Variable squared minus our number. So we have to use a secant theta. If it was the other way around, 16 minus x squared, we would not use this. Okay? Ooh. Yes.
So we could say that for a squared minus x squared, you would always use sine for the substitution. A squared plus x squared is tangent for the substitution. And for the one we just did now, we use secant for the substitution. And will that be true of all of them?
Yes. right here. Anytime you see a squared minus x squared, you always make the substitution x is a sine theta. Anytime you see a squared plus x squared, it's always a tangent theta. Anytime you see x squared minus a squared, it's always a secant theta. 3 cases, 3 different substitutions. And there's no other way you can have a square root of variable squared and number squared. There's no other combination, right? They're either added, or it's your variable squared in front of your number, or it's your number in front of your variable. Those are the only 3 possibilities. But what if it's like square root of a cubed minus x cubed? Bye-bye. This don't work anymore. So this is a very specific technique. That's why later on in this class, when we cover chapter 8, we hopefully we'll come to appreciate the value of the power series when we study power series. Because if you were to take, just speaking in a way that we can make sense out of, if you close your eyes and you reach into the bag of all functions, all real valued functions, and pick one out and lay it in front of you, the probability that you can integrate it is 0. 0. Not even like infinitesimal. 0. So, but if you reach to the bag of functions and you take it out, you say, what's the probability I can integrate it using power series approximation? It's almost assured you can do it. So we learn these techniques, but we're still a one-legged man in an ass-kicking contest. I mean, that's really, at the end of the day, that's what we are here. But it's the whole idea of, think about all the algebra and everything that you have to understand to do this stuff. There's so much math and integration. What's that? Power series? Yes. Yeah, Newton. But once you see it, it's actually not. It's genius. No one's going to argue Newton was a genius, but what makes geniuses geniuses is they make complicated things simple. They make things that we go, how would you ever attack that? And, oh yeah, that kind of makes sense. Wow, why didn't I think of that? Because we're not Newton, right? Okay, let's get into this. Not yet. Maybe someone, someone here will blossom into who knows what. I would encourage you to never give up on yourself, especially if you're making an effort. If you're not trying, crash and burn. No one cares. If you're not putting in effort, no one cares. But if you are trying, don't ever quit on yourself, Don't think that, okay, if I struggle in this math class, I can never be an engineer. If you're really trying, because, sometimes it is a click, it's a switch, and it just flips, and you just, all of a sudden you wake up and one day you're just a better student. And everything lines up for you. But if you don't try, it's not going to happen. I don't know. That's my question to you now. What is it? If you have this form, because that is the form, right? Or the other way around, doesn't matter. With plus, it doesn't matter which order, right? Both of them are going to have the substitution x equals a tangent theta. Does everyone agree? A tangent theta? What's a, though? Square root of 2. So this is our first problem where a is not a nice number. It's nice. Square root of 2 is a good number, right? Okay, here comes my substitution. X equals a square root of 2 tangent theta. That doesn't change the derivative too much, right? It's just root 2 secant squared theta d theta. And then all of this junk turns into the x squared plus 2 under the root turns into a, what is it? Root 2 secant theta. Good.
We always assume that it's always just going to be a and then
Yes. Well, for this it will be. Let me go back to this. This is why that first note was so important. See, I said if you have this form, a squared plus x squared, you'll always have this substitution. Your dx will always be that. And this square root thing will always turn into your a secant theta. You don't have to go through all the work. The yellows are guaranteed every time if that's your original problem. You just need to know what the substitution is, the correct substitution. Everything else, you either memorize it or you create it yourself. I don't know if anyone has ever noticed this in this class, but you see on here, these are the different pages I do. Microsoft Office Note, which is what I use to do notes, it automatically, if I don't title the page, it tries to create a title based off of what I'm writing. So Vitas, I have no idea where Vitas is coming from here. But I'm saying that because I've had a couple of semesters where I write stuff here, and it's like vulgarity over there. Like it's like vulgar stuff. And people are like, what the hell is that over there? And I don't even notice it. So if you ever see anything over there that just looks like, you know, there'll be like something ass or, you know, I have no control over it. FYI. Okay, here's where we are. Now, I'm looking at this integral and I'm realizing that I'm going to need an x to the fifth, right? X to the fifth. Which I just need to take my x here and raise it to the fifth power. So I'll go ahead and do that down here. X to the fifth equals root 2 to the fifth. I'll deal with that later. Tangent to the fifth theta. Just raise both factors to the fifth power. And now I'm ready to go. That'll be this. So my integral becomes integral x to the fifth, we just said was the square root of 2 to the fifth, tangent to the fifth theta. That's just x to the fifth, right? Over, what was that square root stuff down there? Square root 2 secant theta. Okay, and then what was my dx? Don't forget your dx. Square root of 2 secant theta tangent. Oh, secant squared. Oops. Secant squared theta, d theta. So a quick matching here. This is this. This was this top one here. This was this. One of the secants is going to go.
would we ever be able to substitute tangent and secant with what we got earlier before we integrate?
Wait a minute. With what we got earlier.
So if we got x equals x over root 2 equals tangent, we would be able to substitute that before the integral.
You could, but you'd wind up with the original integral. Yeah, each one of those came from that. So if you try and switch back now before the integration, it'll take you right back to where we came from.
Yeah, I was just wondering because after canceling or not, I don't want to deal with all this stuff.
Yeah, this looks like it's not going to be very fun. Let me see. I'm canceling some things out. Some root 2's go away. One of the secants go away. The root 2 to the fifth power is a constant, right? So I'm going to pull that out. I have root 2 to the 5th power. You know what? This is calculus. How about I write that 2 to the 5 halves? Right? Square root of 2 to the 5th power is the same as 2 to the 5 halves. And then I have tangent to the 5th power secant theta d theta. And this is, yeah, this is earlier in this section. So, yeah. No. What I would do is I would go back to what I start out here with. If you have secant and tangent together, if the power on secant is even, it says one thing. If the power on tangent m is odd, factor out a secant tangent. Do I have an odd power on tangent? Yes. So I'm going to factor out a secant tangent. So this equals 2 to the 5 halves integral tangent to the 4th theta secant theta tangent theta d theta. So all I did was peeled off one of the tangents, right? The reason I did that is because secant theta tangent theta d theta is the derivative of what? Secant. So the question is, can you turn tangent to the 4th power into secants? Yes. So this becomes, I'm going to stop right after this. This is just tangent squared theta times tangent squared theta, but each one of those is secant squared theta minus 1 times secant squared theta minus 1. You would distribute that out, get secant to the 4th theta minus 2 secant squared theta plus 1. And then you would distribute, well, then you're ready, pretty much. All of this becomes that. And then it's a basic U substitution with U being what? Secant theta. Dot, dot, dot. Have fun. No bonus. I'll let you finish that problem. I'm not going to take it all the way. What I will do is I'll give you the answer. How about that? The final answer. Even after you do your trig sub back to x, okay? Here's the final answer on this one. Final answer is, which one was this? I'm lost. 1/15 square root of x squared plus 2 times 3x to the 4th minus 8x squared plus 32 plus c. And your answer will probably be this part right here, distributed through to each one. They factor this out. So, but that's what that should all turn out to be. What is 2 to the 5 halves? That's the square root of 2 to the 5th. That's the square root of 2 times 2 times 2 times 2 times 2. Right? All that, 2 times 2, that's 16. Pull out a 4, that's 4 root 2. I'm just showing you what 2 to the 5 halves is because later on, all that ugly stuff goes away and you don't have that root 2 in there anymore. So you'll see what happens. Okay. How we doing? Yeah, this is a good one. This is a good one here. Ready? This is going to end our discussion of trig substitution. This will be our last problem that we do. 1 over the square root of 9x squared plus 6x minus 8 dx. So the floodgates have opened at this point. How do you mean? This does not look like any of the three forms we've had, right? It's not a number squared minus our variable squared. It's not our variable squared minus a number. It's not those added together, right? We seem to have this middle term, right? That 6x really isn't a good thing. But, close. Complete the square. Oh, yes. That was a topic at some course prerequisite to this course, and you probably did it and said, why the hell am I completing the square? Because at Cal 2, we need to complete the square to do this integral. So let's briefly revisit completing the square. Completing the square is this process where you take half of the number in front of x, and then you square it, and then you do something. Do you remember that? It's somewhere buried deep in there somewhere. Okay, here's the thing with completing the square. Most of the time that you're taught completing the square, most of the time it's taught, you're taught when it's an equation how to complete the square. So you're taught, okay, you add this to both sides. The problem is, in calculus, you do not have an equation. You have an expression, right? 9x squared plus 6x minus 8 is an expression. I can't just turn that into equals 0. So how do you complete the square on an expression? Let me take you through it. First things first. In order to complete the square on anything, you must have a leading coefficient of 1, which means the number in front of x squared must be a 1. So I'm going to factor a 9 out. If I factor a 9 out, I get my x squared in the beginning, but I can't take 9 out of 6, so I write it as 6 over 9, x. And then I can't take 9 out of 8, so I write it as minus 8 over 9. Hopefully you've done something like that before in the past. If not, just check it. It's right. Right? Multiply through by 9, you get back the original problem, don't you? I do realize also that 6 divided by 9 is 2/3. I'm just reducing that fraction, just trying to keep my fractions small. Okay, this is all work I'm doing on the side here. Now, the process of completing the square, once you have a leading coefficient of 1, is to take the 2/3. That's the number in front of x. Take half of it. Okay? So what's half of 2/3? So I'm taking my 2/3. I'm multiplying it times a half, which gives me what? 2/6, which is really 1/3. Half of 2/3 is 1/3. That's the first thing you're supposed to do with completing the square. And I'll just kind of box this. I'll need that later. And then you're supposed to take that number and do what with it? Square it. And when you square it, you get 1/9. And that's my second magic number. So what I'm supposed to do now, if you go back into your short-term memory bank or wherever you put stuff, you were supposed to take that number, take half it, square it, and this is where a lot of you were taught add it to both sides. We don't have an equation. So what we do instead is this. Here's our 9. Here's our x squared. Here's our plus 2/3 x. Here's our plus 0. And then here's our minus 8/9. Do you all agree sitting right next to that 2x, 2/3 x? There's a 0 there, right? There is. Believe it or not, this is a pretty advanced technique mathematically to realize a hidden 0 next to something. I think, didn't I allude to this a little bit earlier this semester, or was that my Cal 1 this summer? That was my Cal 1 this summer. I'm sorry. It's all starting to blend together. All right, so realizing a hidden 0 is a pretty big deal. So that's this. Guess what my 0 is going to be? Remember how we were supposed to add something to both sides of an equation back when we were talking completing the square? Well, if I don't have an equation, right, we added it to both sides to maintain balance. So I'm going to do 1/9 in here added and then taken away. I'll put it in red so it'll match up with my 0. So I'm adding the 1/9 and I'm taking away the 1/9. And then I have back here minus 8/9 still. So do you agree? I mean, I have not changed the problem. I mean, this is the same expression. I pulled the 9 out first. Okay, that was kind of weird. And then I did this stuff and it just wound up being, I'm adding it and subtracting it. So I still haven't changed it. But I'm guaranteed now, guaranteed, if I did everything right, the first 3 terms will factor as a perfect square trinomial. Meaning it'll turn into 9. I'm going to do a bracket here. X and then something squared. So that blue is going to turn to x, in parentheses, x and then something and then squared. What's that something? It's whatever that number was over there. The first boxed one. So in this case, positive 1/3. And if you don't believe it, take x plus 1/3, write it side by side, FOIL it out, collect like terms, you'll get this. Guaranteed. So that's the blue. But what's still sitting out here? Minus 9/9? So minus 1? Yeah. That's looking better now. Are y'all with me? Let's go back to the original integral now. And I'll just do it right here. Here we come. The original integral now becomes 1 over the square root of everything that I just got. 9 times bracket x plus 1/3 squared minus 1 close bracket dx. That's just the denominator rewritten, isn't it? What can I do with this 9? Bring it out as a 3 on the bottom, right? What if it was a 5? Bring it out as a root 5. And then kick it out of the integral, exactly. No matter what number is here, you can always take the square root of it. Square root of 9 happens to be a 3, so a 3 comes out, it'd be 1 over 3. If it was a 5, a root 5 would come out and you would have a 1 over root 5. The idea, though, is that you want to get this number that we factored out in the very beginning, you want to get it out completely. Get it out of the root. So that's what I'll do on the next one. 1/3 integral 1 over square root. Now I don't need the brackets. X plus 1/3 squared minus 1 dx. And this is looking mighty close to one of my formulas, isn't it? It's almost looking like my variable squared minus a squared, right? That almost looks like variable squared minus a squared. So to get it to look exactly like variable squared minus a squared, I'm going to do a quick u substitution, just a quick substitution. I'm going to let u be x plus 1/3. What's the derivative of that? Dx. Right? So how could you rewrite this integral then? I'll do it in blue. 1/3 integral 1 over square root. Go ahead now. U squared minus 1 du. Now does that look like variable squared minus constant squared? Yes. You've got to, everything's got to go back to x at some point. Yep. Yep. Okay, so I have the form. Now I'm looking at this. I got the form. It's like the x squared minus a squared, right? What are we supposed to do as our substitution when we have x squared minus a squared? What is it? Secant? Is it a secant? A secant. But it's x equals a secant, right? X equal. We don't have x. What do we have? U. So our substitution is going to be u equals a secant theta. What's a here? 1. Okay, I'm going to move to another page. We were at 1/3 integral 1 over square root u squared minus 1 du. I'm going to let u be equal to a secant theta, which means du is secant theta tangent theta d theta. And then the square root of all this junk, u squared minus 1, is a tan theta. Okay. So just tan theta for us, right? Questions? I'm ready to rewrite integral here. We ready to go? Okay, integral is going to become 1/3 integral 1 over the square root of all that junk is tan theta, right? Oh, beautiful. And then du is secant theta tangent theta d theta. Tangents cancel. So equals 1/3 integral secant theta d theta. Yeah, so natural log. Good, good. You've done enough problems to have that in there already, don't you? Good. So we get it all the way to an integral secant theta, which we have a formula for. The formula is natural log of the absolute value secant theta plus tangent theta, then the 1/3 in front, right? Now let's... What's that?
We already have tangent theta, which is square root of u. And then we also have u, which is...
Do we have secant theta? We do have secant theta? And tangent theta. Nice. So this becomes... Now, I want to flip back so everyone can see where they're coming from. We go back to where we made our substitution. Oh, wait. It was on that page, wasn't it? Oh, it's right there. Damn it. Yeah, there's tangent, there's secant. So we don't need a reference triangle for this problem. Although we could draw one. We don't need one. Then we have to substitute for u. So here's where we go. We are at 1/3 natural log. Secant theta by definition is u plus tangent theta, which is square root u squared minus 1 plus c. Now replace u with whatever u is. It's x plus 1/3 plus over here square root of x plus 1/3 squared plus 1. Oh, minus 1 plus c. Okay? What did you all think of that? Interesting, huh? Completing the square is a technique that we're going to be using on a more regular basis as this class proceeds. Just making sure I've covered what I wanted to here. I don't really want to jump into our next section in the last 18 minutes or so. I'm curious to see what you would want to do with that. Which way would you do that? Like how? You want to just do x squared plus 1 like this? And then du is what? 2x dx? Which you almost have, right? Yeah, so that just becomes integral x dx is 1/2 du. 1 over square root of u, which is just u to the negative 1/2. Basic substitution, done. The point I'm just trying to make is you don't want to get fixated into, oh, I see x squared plus 1, I go to trig substitution. You know, you still want to be thinking. You know, you still want to think. You follow me?
So this one, can we make it x over 1 and then 1 over x squared plus 1 and then turn it into
Wait. Do what? Do what?
inverse? Do you use that anywhere in this?
Can you say it again?
Can it inverse and then 1 over square root of x squared?
No, I don't see how you could do that. Because to use that, you have to truly have like 1 over or constant over.
I was wondering if we take the x and make it x over 1 and then multiply by 1 over that.
I see what you're saying. But then you have two separate integrals separated by multiplication. You can't do those separately.
Yeah, that's what I was thinking.
Yeah.
And then maybe integrate by part if
Yeah.
you want to do that.
Yeah, maybe. So there are several ways. You could do trig substitution on this. You could. For what? For the antiderivative of this? Is it on? Yeah, but you have the x on top. Yeah. So did I kind of make my point here? My point being, we don't want to get too bogged down on any one technique. I assured you of this early on in the integration, that the challenge towards the end is not knowing which technique to apply. Is it just a basic substitution? Is it an integration by parts? You know, is it this? Is it what we're going to do next time? Partial fraction decomposition? It's a lot of them, you know, you kind of know, but I won't spend a whole lot of time on this. Look at that. This is not a basic substitution. You can't just do u is 1 plus x squared because there's no du there. It doesn't look like a trig substitution, but you could square root x squared plus 1 to the 4th power, right? Because if you take the square root and raise it to the 4th, it's the same as raising the whole thing to the 2nd. And now it looks like one of those forms, doesn't it? X squared plus a squared, a being 1. What do we do when we have x squared plus a squared? X is tangent theta, a tangent theta. Dx is secant squared theta, d theta. And this thing turns into secant theta. I'm moving quickly through this because we've done a few, and that all right? Can we rewrite the problem? 1 over, let's see, the bottom is that square root. It's secant to the 4th theta, right? And the dx is secant squared theta d theta. So if you cancel 2 of them, you're left with a secant squared on the bottom, which is really cosine squared. And how would you integrate cosine squared theta d theta? Power reducer, half angle, and then you're in business. Now I want to take this a little bit further because we haven't had one turn out like this, and I think it's important for you to see. Does anyone have a question, though, on where any of that came from? All right, going back now, this turns into two different terms. 1/2 plus 1/2 cosine 2 theta d theta. So I used the half angle identity, or what I call the power reducing formula on cosine squared theta from last class, turns into those two terms. Now integrate each of those two terms separately. Go ahead. What do you got? Question? Sure?
The air rule, the 1/2 theta, would we do like we did on that one tangent problem?
Yes. Yep, that's why I want to do this. Okay, when I integrate 1/2, I get 1/2 theta. When I integrate 1/2 cosine 2 theta, I get what? 1/4 sine 2 theta? Plus a constant. There's 2 things to notice in this problem. First of all, we need to know what theta is, right? And what do we have? What information do we have between x and theta? Right there, right? That's our relationship between x and tangent. X and theta. Yes, yes. If you mean turn cosine squared theta into 1 minus sine squared theta? Because then what do you do with sine squared theta? You basically would be in the same position. You would have to do something with sine squared theta, which would be power reducing on that. Remember, if you have sine or cosine to an even power, power reduce formula. All right. I'm going to write my relationship down here. I had x was equal to tangent theta. No. Yeah? Yeah. Okay, x was tangent theta. Yes, I'm going to create a reference triangle. Here it comes. Here's theta. Tangent is opposite over hypotenuse. Wait, opposite over adjacent. I like to ask this just because I'm curious to know how many of you learned SOHCAHTOA. How many of you learned SOHCAHTOA? So it's still being taught quite a bit, SOHCAHTOA. Anyone not heard of SOHCAHTOA? It's this Indian, old Indian girl who was very good at geometry. Her name was SOHCAHTOA, right? SOHCAHTOA. It is probably very racist, and I apologize, but it's a true story. If it wasn't true, then it wouldn't, if I was making it up, it would be racist, but it's true. SOHCAHTOA is what Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. SOHCAHTOA. There you go. You probably will never forget it. Just like ultraviolet minus voodoo. Okay, so wait a minute. Hold on. I'm lost. That's my relationship. I need theta, right? I need theta. So how do I get theta from that equation? Take the inverse, right? So the arc tangent or inverse tangent on both sides. So that becomes 1/2 tangent inverse of x plus 1/4. Be very careful here. I need to know what sine of 2 theta is. Not sine of theta, sine of 2 theta. No, you cannot factor the 2 out. But you can use your double angle identity. Remember what sine 2 theta is from pre-cal? Of course, it's 2 sine theta cosine theta plus c. Now, do you know what sine theta is? Go to your triangle, opposite over hypotenuse. We don't have our hypotenuse. Now we do. Okay, so sine will be what? X over that square root. Cosine will be 1 over that square root. Well, it's going to take care of itself. Watch. And this is going to become the 2 over 4 is just 1/2. Sine was x over square root x squared plus 1. Cosine was 1 over square root x squared plus 1 plus c. So this is 1/2 our tangent x plus 1/2 x over x squared plus 1 plus c. And we are done.
When you write arctan, it's ARC, right?
ARC. ARC.
Okay.
Mhm.
Make sure.
Yep. And from my understanding, the only reason why there's 2 notations is because the -1 historically has represented the inverse function. But if you ever had to type up a paper using a superscript, it's hard to superscript. So it's easier to say type ARCTAN. So it's just a typesetting thing to make it easy. I'm going to let you go because we only have a few minutes, but I want to take a poll before I start thinking about next class. I want to take a poll on, how many of you in pre-cal saw something like this? Let's say I have 2 over x. Well, you know what? Let's do it off this. Had seen something like this. You have 1 plus 6x. You don't need to write any of this down ever. Okay, just follow me for a second. How many of you have seen that when you have something like this, that you can take it and turn it into like an a over that 4x minus 3 plus a b over that 2x plus 5? It's called partial fraction decomposition. So let's see, big show of hands. Okay, if I were you, along with the homework you do, if you feel uncomfortable with this stuff, you should go back and look at it before class, because I'm going to be doing partial fraction decomposition. And it's going to be a lot worse than this, because we're going to go and look at things that you probably haven't seen. And so you've got to kind of have this down already. We'll be doing things like make this one a cubed on that, or make this inside here a quadratic instead of a linear factor. How about solving systems of equations? Things like this. Let's say I have 2a plus b minus c equals 5. Then I tell you that negative 4a minus 2b plus c equals 10. Right? And then another one. Let's say another one. How many of you know how to do that on your calculator? Are you serious? Only 2 people would know how to solve a system of linear equations on their calculator. Okay, how many of you don't have a TI graphing calculator? Who does not have a TI graphing calculator? Do you have any graphing calculator? Anything? Nothing? Do you? What do you have? But I'm saying, like, for in class, do you have anything? No? No? Non-graphing? Okay. Here's the deal. This class does not require a graphing calculator, but there are going to be problems in here where we're going to have systems of equations with, this has 1, 2, 3 variables. We may have 5, 6 variables, 6 equations, which by hand would be a disaster. It would take you 45 minutes just to find the solution, okay? So what I'm going to do is, for the time being, for anyone who does not have a TI or some smart calculator that can do this for us, I'll let those people maybe work on the computer, but try in the next couple of weeks before our next test to get your hands, borrow it from someone, you know, see if you can get a graphing calculator. I don't want you to go spend $100 on one, but see if you can get one, even if it means just for the day of the test. Okay? So I saw it online. Yeah. Craigslist. Yeah. You don't need a TI-89 though. I mean, you just need a basic. See, some of the TIs won't do it. What you have to have is somewhere in there, it has to have this function, RREF. If your calculator has that, yep, reduced row echelon form is what it stands for, linear algebra people. Okay, reduced row echelon form. So if your calculator can do that, then you can solve, 30 equations, 30 unknowns, or even higher. So these are just 2 things, being ready for next week. Maybe take a look at that a little bit. Take a look at this. Homework, who has got let me see it real quick. I'm sorry, I don't know how I ran out of time. I seemed like I had all this free time, and then I ran out of time. Let me tell you what you should do. Finish up 6-2. 43 through 6. No, not 63. That's 43 through 59 odd. And then, of course, do the evens if you get that done. 49. Wait, did I say 49? 43 through 59. I'll tell you in a second. Odd. This is page. Was this the right book? Yeah. Page 326. Let's do a quiz on Tuesday. First thing, your 6.2 homework. Have it out. And I'll come around and give you 2 quiz grades off of your homework.
So for that and the previous one, for 6-2, the entire 6-2, right?
All of 6, everything I've assigned for 6.2, have it ready on Tuesday. It'll be worth 2 quiz grades. Yeah, it may not have it. I'll show you. It's under matrix. Let me turn off my video.